Okay, in this class we will discuss about discrete Fourier transform DFT. You are aware about the discrete time Fourier transform DFT, which is defined as x omega is equal to x of n e raised to power minus j omega n, and this Fourier transform has a property that x omega is same as x omega plus 2 pi. Okay, it means in the frequency domain the frequency spectrum repeats with a period of 2 pi. So whatever is the spectrum between 0 to 2 pi, the sum is between 2 pi to 4 pi, then 4 pi to 6 pi, and so on. Okay. And although the sequence xn itself is discrete in nature, its Fourier transform is a continuous function of frequency. Okay. So when you say DFT, DFT is basically obtained by sampling its discrete time Fourier transform. So if you take the samples of the discrete Fourier transform, discrete time Fourier transform in the frequency domain, you get DFT. Okay. And in that sampling process, we will concentrate only within the band of 0 to 2 pi, because the entire information in the frequency domain is available within this band only. Okay. So we start from xn. You take its DFT, you get x omega, which is its Fourier transform. We call it discrete time Fourier transform. And then we sample it in the frequency domain. We take the samples of x omega, that is samples of DFT. Those samples we call them as DFT, discrete Fourier transform. And you must have a relation, you must develop a relation so that you should be able to recover x of n directly from the samples of its Fourier transform using inverse transform, that will be IDFT, inverse discrete Fourier transform. Okay. So this relation we will first develop, that how to sample the Fourier transform in the frequency domain to get DFT, the samples of Fourier transform, and then how should you choose the samples in the frequency domain so that you should be able to recover the original signal axon directly from its samples. Okay. So let us start with the sampling of the spectrum. Sampling of DTFT. So you have x omega, x of n e raised to power minus j omega n. And now we take only a frequency band of 2 pi, because after 2 pi it is repeating. So 0 to 2 pi. Okay. So between 0 to 2 pi, suppose we take now its samples. We take the samples of Fourier transform in the frequency domain. And we will see that how we should be able to recover x of omega back from its samples. Okay. Let us suppose we take equispaced samples. Okay. And between 0 to 2 pi, suppose we choose n samples. Okay. Between 0 to 2 pi, if you choose n samples, so the spacing between the two samples will be nothing but 2 pi by n. Okay. It means you're getting first sample at 0, then at a frequency of 2 pi by n, then 4 pi by n, then 6 pi by n, and so on. Okay. So this omega in the DTFT, which is continuous function, it will be simply replaced with 2 pi k by n. Okay. Where k is 0 1 up to n minus 1. So you are choosing n samples. So in case 0, you are getting the first sample at 0 frequency. In case 1, you are getting the second sample at 2 pi by n, then 2 pi 4 into 2, 4 pi by n, and so on. So this equation, when you sample it, the samples you will get simply 2 pi k by n, and that will be x of n e raised to power minus j 2 pi k by n into n. Okay, and then we do some modifications here. What we do, we write this series as a sum of another infinite summations each having n terms. Okay, means I write it out like this. I take first n samples 0 to n minus 1, x of n e raised to power minus j 2 pi k n by n. This is one series. Then I take next n samples, that is start from n to 2n minus 1. Again x of n e raised to power minus j 2 pi k n by n. This is second series, and so on. Similarly, in the negative side, you can take. Okay, in the negative side, you will get n from minus 1 to minus n, first sum, then so on. Now, this infinite series, which is decomposed into sum of different summations, each having n terms, you can express this in the form of a double summation like this. You can take it L from minus to plus infinity and n from Ln to Ln plus n minus 1 x of n e raised to power minus j 2 pi k n by n. Okay. So for each value of L in the outer summation, you will get each term or each series in this. Suppose when L is 0, for L is equal to 0, if you open the inner summation of n, your n will be 0 for L is equal to 0, and upper limit will be, when L is 0, it will be n minus 1. So for L is equal to 0 in the outer summation, you are getting this series, first term, first n terms. Then if you put L is equal to 1, you are getting the next n terms, n to 2n minus 1, and then so on. Okay, so we have now x 2 pi k by n. I have written it as double summation, 1 for L from minus to plus infinity, and n from Ln to Ln plus Ln minus 1 xn e raised to power minus j 2 pi k n by n. Okay. Again, in this series, in this summation, we change the order of summation from n to, suppose, p is equal to n minus ln. Okay, in the book it is written n minus ln, but that creates sometimes confusion. I have used a summation n is equal to ln. The variable is changed from n to p, with p is n minus ln. So you will get L from minus to plus infinity, and p. And when n is ln, your p will be 0. And when your n is ln plus n minus 1, your p from this equation will be n minus 1. X of n. Now n will become p plus ln, right? And e raised to power minus j 2 pi k by n. Again, this n will become p plus ln. Okay. And if you interchange this order of summation here, I first write, suppose p is equal to 0 to n minus 1. Then L is equal to minus 2 plus infinity x of p plus ln e raised to power minus j 2 pi k p by n into e raised to power minus j 2 pi k by n into ln. Okay, I opened this. You are getting two different terms here. And if you look to this term, your n and n will get cancelled, and kl, k into l, this is nothing but integer. Okay, so e raised to power minus j 2 pi kl, it is cos 2 pi kl minus j sin 2 pi kl, which is nothing but 1. So this term will become 1. Okay, so as a result, you will get only summation of p from 0 to n minus 1, summation of l from minus to plus infinity, x of p plus ln e raised to power minus j 2 pi k p by n. And again I change this variable p to n. Okay, so it will become n from 0 to n minus 1. This is I'm using just in order to be consistent with your what is given in your textbook. Okay, otherwise you can keep it p also, no issue. It will be n plus ln e raised to power minus j 2 pi k n by n. Okay, now if you see carefully to this inner summation, x of n plus ln, l from minus to plus infinity, what you will get? When l is 0, you're getting xn, or you can say it is nothing but like this, x of n plus x of n plus capital N. When l is 1, when l is minus 1, it is capital X of n minus capital N, and so on. Then x of n plus 2n, and so on. This summation for l. Okay, so if I take xn, if you take xn like this, suppose you have xn sequence which is 4, 3 and 2, 3 samples. Okay, and if your n is 5, so what is x of n plus n? It is the same sequence shifted by 5 samples to the left. What is x of n minus 5? The same sequence shifted by 5 samples to the right. It means you are getting this 0 will be shifted to now 5. So at 5 you have 4, 3, 2. Similarly, in this case it is shifted by 5 samples to the left. So you have 2 zeros here in between, and so on. Okay, so when you add all these, x of n plus x of n minus n plus x of n plus n, and so on, what you are basically getting is a sequence which is periodic with a period of n, and this periodic sequence is nothing but the repetition of xn after every n samples. Okay, or you can say it will become like this. Suppose it is 4, 3, 2 xn, and if n is 5, it will repeat up to 5 samples, the same sequence. It means you will get 2 zeros, then again 4, 3, 2, then 2 zeros, 4, 3, 2, 2 zeros, and so on. This we denote it by suppose xpn. So xpn is my periodic sequence, okay, which is obtained by repeating xn after n samples. Okay, now since this sequence xpn is periodic, I can write its Fourier series. Okay, so xpn, for this sequence I can write the Fourier series like this. Xpn, its Fourier series will be summation of k from 0 to n minus 1 ck e raised to power j 2 pi k n by n, where your n is from 0 to n minus 1. And what is the ck, which is the Fourier series coefficient? It is given by 1 by n summation of n from 0 to n minus 1 x pn e raised to power j minus j 2 pi k n by n, where k is from 0 to n minus 1. Okay, this is xpn, okay, and this is ck. So if you compare these two equations, this equation and this equation, what you'll get, you can simply write ck as 1 by n, and this is same as your this equation, okay. So I can write it as x of 2 pi k by ck. This is a very important relation, okay. And finally, if you put this ck in this equation, you will get equation for xpn. So xpn will be equal to 1 by n, that will come from this 1 by n summation of ck. So ck, in place of ck, you can write it now as x of 2 pi k by n multiplied with e raised to power j 2 pi k n by n, where n is from 0 to n minus 1. So this equation, what it gives you, and this range is for k from 0 to n minus 1, okay. So what this gives you, this equation gives you a reconstruction formula from the samples of its Fourier transform. And remember that you cannot recover xn from the samples. What you can recover is xpn, okay. I will write on different page. So what we have done, we have taken f first x omega, which was summation of x of n e raised to power minus j omega n. This is your DTFT. And then we have sampled it. We have taken equidistant samples in the frequency domain with a spacing of 2 pi by n. Okay. And this equation we finally got like this. It was n from 0 to n minus 1 x of pn e raised to power minus j 2 pi k n by n. Okay. Where k was from 0 to n minus 1. And this xpn is nothing but a periodic sequence. We have taken its Fourier series and an inverse Fourier series, and then finally we have got that xpn can be written as 1 by n summation of k from 0 to n minus 1 x 2 pi k by n e raised to power j 2 pi k n by n for 0 to n minus 1. So this equation, it gives you the samples of Fourier transform, and this equation, it gives you the time domain sequence back from the samples of the Fourier transform x omega 2 pi k by n. These are nothing but the samples. So using the samples, how can you reconstruct the sequence in discrete time? But you must remember here that you are recovering xpn from its samples, not xn, okay. And then you have to simply see that how you can recover xn from xpn, okay. And that is very simple. It means you have a sequence xn, you have taken its Fourier transform x omega. Between 0 to 2 pi, you have taken its samples with the spacing of 2 pi by n. You have taken n samples. You got this equation. Now from these samples, when you apply this inverse relation, you are getting xpn. It means from the samples, you cannot directly get xn, but what you can recover is xpn. So xpn is what? Xpn is the periodic sequence which is obtained by repeating xn after every n samples. Okay, now you take two different cases. I suppose I take xn as a original sequence. This is 4, 3, and 2, 1. Suppose it has 4 samples. Okay, now I take its DFT. I take its DTFT. What I will get? It has some spectrum which will repeat after 2 pi. So between 0 to 2 pi, it has some unique spectrum. Okay. Now let's take the samples in the frequency domain. Samples of its DTFT. Now from these samples, what I can recover is xpn using this equation, not xn. And what is xpn? It is the same sequence repeated with n. So suppose in one case I take n is equal to 5, and in the second case I take n is equal to 3. It means I am taking 5 samples in one case in this frequency domain. Now when you take 5 samples in the frequency domain, what you will get in the time domain? You are getting 4, 3, 2, 1. The sequence will repeat after 5 samples. It means you are getting 1 0 here, then again 4, 3, 2, 1, then 0, 4, 3, 2, 1, 0, and so on. This is what is my xpn. And see, from this xpn I can simply get xn back if you just take the first 5 samples. Okay, if you just take the first 5 samples, last sample is 0, I can simply get the first 4 samples, that is xn. But if I take n is equal to 3, what I will get in the xpn? In the xpn I will get the same sequence repeated with 4 samples, sorry, 3 samples. It means I will get 4, then 3, then 1. Okay, this will be repeated by 3. So if you repeat this by 3 samples, so when you next repeat it, it will again become 4, 3, 2, 4, 3, 2. So this last sample 1 will be lost. Okay, so as a result, from this xpn I cannot recover xn. It is not possible. Whereas if you take n is equal to 5, there is 1 0, then the signal repeats, then 1 0, then signal again repeats. So from this sequence I can simply recover xn if I just take its first n samples. Okay, so what is the condition for sampling in the frequency domain? It means the number of samples. If xn has a length L samples, so n must be greater or equal to L. The number of samples in the frequency domain, that must be greater than or equal to the length of the signal. Then only you can recover xn from its samples. Otherwise it is not possible. Okay, so it is the same case as in the time domain. You have seen when you sample the signal in time, it repeats in frequency. Okay, and when you sample the spectrum in the frequency, the signal repeats in time. It is xpn that you can get, not xn. Okay, and from xpn you can simply get xn if you just take its first n samples, provided you have chosen the number of samples which is greater than or equal to the length of the signal. Okay, so it means if you have a discrete sequence, xn with 8 samples, so in the frequency domain you must take minimum 8 samples, so that from the samples you should be able to recover xn back. You cannot take 6 samples or 5 samples. You can take more than 8 samples, no issue. You can take 10 samples, you can take 16 samples, you can take 100 samples, that is okay. But the minimum number of samples must be 8. If you take less than 8 samples, there is a aliasing in the time domain. Okay, so when you sample in the frequency domain, you get aliasing in the time domain. When you sample in time domain, you get aliasing in the frequency domain. Okay, so I conclude this here, that your sequence xn, if you take its Fourier transform, which is given by this equation, which is continuous spectrum, and when you take n samples in the frequency domain using this equation, so from these samples what you can reconstruct is a periodic sequence xpn, which is obtained by repeating xn after every n samples. So in order to avoid any aliasing distortion in the time domain, the number of samples must be greater than or equal to the length of original signal. Okay, so this is how you sample in the frequency domain and how you recover the signal from the samples in the frequency domain. Okay, in the next class we will discuss that how you can we will see a interpolation formula again, that how to recover x omega directly from the samples of x omega. Okay, right now we have discussed the equation to recover the signal in time from the sample in the frequency, this equation, but you will develop a relation in which you can directly recover x omega from the samples of x omega. Okay, and then we will define formally what is DFT and what is IDFT and other properties.